Okay, here we have the second walkthrough for the foundation stroke higher chemistry AQA paper. So question 1, rates of reaction, looks at the sodium thiosulfate reaction and hydrochloric acid where the cross disappears because there's a precipitate of sulfur released during this reaction. Talks a bit about the experiment here. The first thing it asks us to do is draw a line of best fit on the graph. So obviously you're going to use a nice sharp ruler and a ruler and a nice sharp pencil. There we go. You want to go as close to as many points as possible and have the same number of points above the line and below the line. There is perhaps one anomaly there that we might discuss in a second. So just two reasons why all of the points do not lie on the line of best fit. Well, you could have had anything like a timing error, you could have had error taking the measurement, you could have had temperature fluctuation, and plotting error. So anything reasonable really, lots of things you could choose from, but these are the main ones, so only two of those would be great. In a conclusion to the investigation, the student stated that the rate of reaction is directly proportional to the concentration of the sodium thiosulfate solution. How does the graph support this conclusion? So we're looking at our graph. It's a straight line through the origin with a positive gradient. So that ticks all the boxes for direct proportional. So straight line, through the origin, or 0, 0. There we go. Explain in terms of particles why the rate of reaction increases when the concentration of sodium thiosulfate is increased. So you have more particles per unit volume, so it's nice to put that, but not necessarily one of the marking points, which means you have more collisions and hence the reaction happens faster. Question 2 looks at rate of reaction again. So a student investigated the rate of reaction between magnesium and dilute hydrochloric acid. The student used the apparatus shown in figure 1 to collect the gas produced. So we have a gas syringe which is collected via a delivery tube to a conical flask with a bung with a hole in, connecting the delivery tube to the flask. You've got some dilute hydrochloric acid and some magnesium in here. So we need to outline a plan to investigate how the rate of reaction changed when the concentration of hydrochloric acid was changed. So first thing you'll do is remove the bung, add the magnesium, and start your timer. You would measure the volume of gas produced at fixed intervals. So every minute or so you could read out how much gas has been produced on the gas syringe, record that in the table. Do this for about 3 or 4 minutes until the reaction is finished. You would then repeat it acids, and things you'd keep the same. You would have the same volume of acid, you would keep initial temperature constant. So the temperature will fluctuate a little bit during the experiment because it's an exothermic reaction, but we can't really control that. What we can control is that initial temperature, and mass or surface area of the magnesium. B shows us a gas syringe during one of the experiments, and we have to just read off there and determine how much gas has been collected. So I might take my ruler here, draw that, and I would say that's probably 6.5. So that's the 5 mark, there's 10, so 6, 7, 8, 9, yep, 10, so 6.5. Next it shows us the students' results for one concentration of hydrochloric acid, and on the following page it gives us a table, so it's a little bit awkward because these are on different pages, but we'll see how we do. We have to plot this graph. The concentration was 2 times greater than the first result, so the acid was significantly more concentrated. So first was 0, 0, and then it was 0, 0 for the first one, and then it was 10 and 35. So we go along 10 up to 30, and then there's 35. Next one was 15, 52. So along to 15, and that will be 52 there. Next was 20, 80. So along 20 up to 80, and the last one 30, 87. So 30, 80, I think 7 there. Okay, and it asks us to draw a line of best fit. Again, we go as close to as many points as possible, equal numbers of points above and below the line. That's not bad. So you can see we've got 1 or 2 anomalies here. Give one conclusion about how the rate of reaction changed when the concentration of hydrochloric acid was changed. Well, if we look at the graph, the line was a lot steeper, the reaction happened in a lot shorter time, so you can say the rate of reaction is a lot higher. So the higher the concentration, the faster the rate of reaction. So question 3 looks at the structure of the Earth and the atmosphere. If we read the bit here, it says scientists believe that the Earth's atmosphere was formed by volcanoes releasing gases. The early atmosphere was about 95% carbon dioxide. The composition of the Earth's atmosphere is always changing. So the Earth's atmosphere today contains about 0.035% carbon dioxide. So what's happened to the most of the carbon dioxide that was in Earth's early atmosphere? So first thing, we can say it was taken in by plants during photosynthesis. We could then say it was absorbed by the water in the oceans. So carbon dioxide is soluble in water to a certain extent, and then finally it was locked away in sedimentary rocks such as limestone or even fossil fuels. Next question. About 60 million years ago, a large meteorite hit the Earth. This heated the limestone in Earth's crust, causing the release of large amounts of carbon dioxide. So calcium carbonate, which is limestone, so CaCO3, undergoes thermal decomposition, so breaks down in the presence of heat, to release carbon dioxide. So breaks down to form carbon dioxide. So key marking points here are calcium carbonate and thermal decomposition. Those are the two marks. Next we have a graph. This graph is showing the percentage of carbon dioxide in the Earth's atmosphere over the last 50 years. So, and the question below asks us to explain as fully as we can why we should be concerned about the information displayed on this graph. So percentage, so the most important, the most worrying thing is the percentage of CO2 in the atmosphere is increasing, it's going up. So starts around 0.315 and it's steadily been increasing over the last 50 years shown in this graph. Another thing to note is the increase is getting more rapid, so the situation's been getting worse over the last few years. So it started out quite a gentle increase, and as you can see it's got steeper and steeper and steeper, so it's definitely getting faster. And the last marking point will be for saying that CO2 contributes towards global warming, which is bad. Next we're looking at a bit about moving continents. So it suggests why most scientists in 1915 could not accept Wegener's idea of continental drift. Lack of evidence. These sort of things almost always lack of evidence. Use the information above and your knowledge to explain how continents move based on this diagram. So heat from radioactivity in the core causes convection currents in the mantle, and this causes the tectonic plates to move. So you have the heat might happen somewhere like this, which will cause the mantle, this area here to heat up. It heats, it expands, it becomes less dense, so it starts to rise. When it reaches the crust, it's got nowhere to go apart from sideways, so these currents drag the tectonic plates, which are sections of the crust, in different directions. So obviously these ones will both move that way, and you'd have a region there that would probably have a lot of volcanoes in, and a new land would be created here, interestingly. Okay, here you have question 4. It talks about a power station and fossil fuels being burnt at some power stations. It asks us how fossil fuels release their energy. Well, they do that via combustion. So the hydrocarbons join with oxygen to release water and carbon dioxide, so combustion. Problems are associated with this one. You have carbon dioxide that's released during combustion, which contributes to global warming. Nitrogen oxide goes to acid rain, and solid particles, global dimming. Question 5 looks at the fractional distillation of hydrocarbons or crude oil. We've got a picture of some equipment here. We have some heat being supplied below, probably by a Bunsen burner. We have a water bath here, so it's not being heated directly. You have the liquids in a fuel inside here. Here's your evaporating flask. You have a thermometer. The heat would cause this to evaporate, go up through here, and it would condense in this part here, and drip down into our beaker. W, well, we've just talked about that. It's the flask. What is the name of this method of separation? So we're separating liquids of different boiling points, and the name for that is distillation. So what is this method of separation? It's distillation. Name the changes of state taking place at A and B. So we'll flick back to have a look at the diagram. So A, so you have evaporation happening at A and condensation happening at B. So boiling, so evaporation not an option, boiling is another word for that, and condensing here. Which hydrocarbon will be last to collect in the beaker? So we're looking for the one with the lowest boiling point, so one that's going to stay the gas the longest. So pentane's got the lowest boiling point on our list, so pentane. The fuel is a mixture of liquids that has been designed as a useful product. So a mixture that's been designed as a useful product, that is a formulation. How is it different from crude oil? So the fuel is a mixture, kind of like crude oil, of only 4 fuels. Crude oil is a mixture of many more fractions or many more compounds. Hydrocarbons. Last part of question 5. The students measured the melting point of a solid hydrocarbon 4 times. Here are the students' results. So let's have a quick look along these. We've got 35, 48, 37, 37. So these results are quite close to each other apart from one. So I think this one here is an anomaly. These ones 35, 37, 37, quite close together. We'll call those concordant. If we have something that's clearly an anomaly, what we do is just get rid of it, we ignore it, we pretend it never happens. If we can redo the experiment and take another reading to replace that, then we will do, but in this instance we'll just calculate the mean without it. So we've only got 3 readings now, so we'll be doing 35 plus 37 plus 37 all over 3. Let's see what that comes out as. Get a trusty calculator. 35 plus 37 plus 37 over 3, 36.3 reoccurring. Now it is asking for us to give it to 2 significant figures, so I'm going to write that as 36, and again let's underline it to show the examiner what he's marking. So our next question, question 6, is about drinking water. The flow diagram below shows how water is made suitable for drinking. So we start off with water in the reservoir, it's filtered, it's sterilised, and then we can drink it. First part asks us what is removed when the water is filtered. So it's anything solid, particulates, but solids what we're looking for, we're separating liquids from solids. What is used to sterilise the water? So we can use chlorine. Why do we sterilise water? Well, we're trying to kill or remove any harmful microbes or bacteria. Water can be purified by distillation, so we looked at distillation in the previous question. We can purify water like that, but it's expensive. And the reason it's expensive is because it requires a lot of energy, lots and lots of energy. So we have to heat the water till it boils and then let it condense again. So obviously we're heating it from room temperature around 15, 20 degrees, 23 degrees, all the way up to 100, so lots of energy. Why do some water companies add fluoride to drinking water? That is to improve dental health. So fluoride is good for your teeth. So it's good for your teeth. Okay, so we've got question 7, looking at methods of separation or chemical analysis, chromatography this time, and we're investigating the colours in different inks. So figure 1 shows the apparatus the student used, and it's told us already that they've made 2 mistakes. So if we have a look at our diagram, yeah, it's pretty obvious here. The first thing they've done is they've drawn their start line in ink, and that would cause the ink to, so the line would run when the solvent soaked up the paper. Also, the solvent, their water, is above all the samples, so as soon as you put this in there, the samples are just going to wash off. So let's jot that down. So first mistake number 1, the line drawn in ink should have been pencil, so ink not pencil. So the line would run. It's not what we want. Mistake number 2, so the start line was below the solvent. So samples would wash off. Not good. Next, they realised they were making a mistake. They've done it again. They've done it right this time. No more mistakes. And it's asking us what colours are in the black ink. So this is the black ink. This is the one we're testing, and we can see that this dot here matches up with this dot. So we've got some red ink, and then if we go up, we've got another dot, and that matches up to the blue ink. So we've got red and blue, and you would need to get both of these to get the mark. Which of the inks is most soluble in the solvent, and give a reason for your answer. So what we're looking for is the one that's travelled the furthest. So this one here, the yellow ink, has travelled the furthest. So the one that's most soluble, yellow, because it's travelled the furthest. Okay. Next, use figure 2. So it looks like we're going to have to do some measuring with a ruler here to complete the table below, and then calculate the RF value for red ink. So first thing, we're distance moved by the red ink. Let's have a look. We'll take our ruler. This is our red ink, and if we go to there, that looks to me the maximum distance it's moved is 9mm. And the distance from the start line to the solvent front. So here's our start line, and it's a little bit faded here, but there's our solvent front, and I think we're looking at approximately, well, no, we're looking at exactly 28mm. So I've just recorded those numbers there, 9 and 28. To work out our RF value, it's been very nice in this paper. It's given us the equation, distance moved by red ink over the distance moved by the solvent. So RF is going to be 9/28. Big number divided by a little number. Always remember that if they don't give you the equation. 9/28, 0.3214. And it's asking for 2 significant figures, so I'm going to give it as 0.32. And again, write it down here just to be on the safe side, to show the examiner this is what he's marking. How can you tell from figure 2 that the RF value for blue ink is greater than the RF value for red ink? Let's just move further up the paper. So the closer you are to the solvent front, the further you've moved up the paper, the greater your RF value. So question 8, we're looking at combustion. So we're investigating the substances produced when fuels burn. So if we're burning a hydrocarbon, if we burn a hydrocarbon with oxygen, it usually produces carbon dioxide and water, but I think this is going to be a little bit more complicated. So we've got our fuel burning here, and the products of that combustion are trapped by this funnel. They travel along this delivery tube through a U-shaped piece of equipment, through some icy water to cool it down, and then through an indicator, and then finally out to a pump where it gets sucked in. So looking at the figure, above, what would you expect the student to see in tube A? So what do we expect to see here? I'd say we'll see a colourless liquid, which would be water. So that's one of our products of combustion. When the student burned the fuel, she saw soot in the funnel. So soot happens because we've got incomplete combustion. So we've got incomplete combustion, and that happens if we haven't got enough oxygen. So due to lack of oxygen. So if we had plenty of oxygen, your candle would be burning, your burner would be burning with a nice blue flame and you'd get no soot. But obviously this person isn't getting enough oxygen, so incomplete combustion. The student burned another fuel which contained impurities, so it wasn't just a pure hydrocarbon. The substance in tube B is water containing universal indicator, which turned red. Now when universal indicator turns red, that means there's an acid present. So if there's an acid present, it's probably caused by something like sulfur dioxide or nitrogen dioxide, which joins with water and forms what we call acid rain. So if we have a look at our options, yeah, here we go, look, sulfur dioxide, definitely that one there. Question 9 looks at the viscosity, so the thickness, the ease at which they flow of liquid hydrocarbons. So as it says here, a viscous liquid is a liquid that flows slowly. The student uses this method, so they measured 50 centimeters cubed of the hydrocarbon, put it into a funnel as shown in figure 1 down here, and then they times how long it takes for all of the liquid hydrocarbon to run out of the funnel, and they repeated this for different hydrocarbons. Apparatus A is a conical flask, because it's a flask shaped like a cone. Name the apparatus that could be used to measure 50 centimeters cubed of liquid hydrocarbon. So the most obvious thing that springs to mind is a measuring cylinder. You could also use a pipette or even a burette. So this pipette and the burette are probably more accurate than using the measuring cylinder. Next we have a table full of data here. We have the different hydrocarbons of different chain lengths. So the first one's got 5 carbons all the way up to 12. Did the experiment 3 different times and they calculated the mean time in seconds for each result. They've missed out the one for septane, so C7H16, so I imagine we probably have to calculate that in a second. And there's also a circled value around here which suggests this might be anomalous, and looking at the other results around it, yeah, that probably makes sense. And what have we got? So the student did the experiment 3 times with each liquid hydrocarbon. Suggest why. So why did we do it 3 times? So we can use the multiple results to identify anomalies. We could also calculate a mean average, and both of these things will improve accuracy. So our results are going to be closer to the true value. Use the data in table 1 to calculate the mean time in seconds for C7H16. Yeah. So we have a 19, a 20 and an 18. So let's write them down here. So a 19, a 20 and an 18. So to calculate a mean, you just add the 3 values together and divide by how many there are. Pop that into the calculator. So 19 plus 20 plus 18 equals, divide that by 3, 19. So 19 seconds. Again, write it in that slot there, make sure the examiner knows what they're looking for. Complete the sentence. As the number of carbon atoms in a molecule of liquid hydrocarbon increases, the time taken for the liquid hydrocarbon to run out of the funnel increases. So the more atoms there are, the longer it takes. So a ring has been drawn around one result. I think this is the one we mentioned earlier. The result has not been used to calculate the mean time for C10H22. Suggests why this was not used. The result was an anomaly. Didn't fit our pattern. Didn't agree with the other bits of data, so we won't use it. Suggest one error the student may have made to get the ringed result. So he might have used a shorter chain carbon by mistake. Could have started timing late. The volume of hydrocarbon too small. So they're looking for anything reasonable really, but it has to explain why the timing was short rather than long. So it has to agree with what the anomaly looks like. So C, the students investigated the effect of temperature on the viscosity of one of the liquid hydrocarbons. There are quite a lot of hazard symbols. So this one means it's flammable, this one means it's an irritant, this one means carcinogenic, and this one means harmful to the environment. So why we wouldn't use a naked Bunsen burner flame? Well, it's flammable. If we use that, it would catch on fire. I'll try and spell that correctly. Flammable. The student wore safety glasses. Anything else we could do? Well, it's an irritant and it's carcinogenic, so I'd probably wear gloves, as it is an irritant or carcinogenic. So just a side note, carcinogenic, so this symbol here means cancer causing, so it causes cancer. On to D. So this is the method the student used to investigate the effect of temperature on the hydrocarbons. So measure the 50 centimeters cubed of liquid, pour it into a beaker, stand the beaker in a heated bath, leave it for a few minutes. Measure the temperature of the hydrocarbon, pour it through the funnel, time how long it takes, and then repeat at different temperatures. So this is what the student did here. So we've got a set of results. So this is the range of different temperatures. This is the time taken for it to run out of the funnel. We're going to have to plot this on our axes over here. So first one was 23 across and 27 up. So 23, 27 here. It's given us a nice scale to plot. Next one we had 30, 21. So 30 up to 21. Then we had 37, 17. So 37, 15, 16, 17. 46, 16. So 46 here up to 10, 15, 16 there. 55, 11. So 55, that's 10, 11, and 65, 9. So 65 up to 9 there. Okay, so I think that's not too bad. We've got a little bit of an anomaly there, and we have to draw, let's say, a nice curve that goes down here like that. Not the best curve, sorry about that. Yeah, well look, there's our anomalous point. It's asking us to draw a ring around it, or many. Predict how long it will take the liquid hydrocarbon to run through the funnel at 70 degrees C. So this is 70 degrees C. Let's draw a line on this with our pen. So we'll go up from 70 till we hit the line. That's the line. And across. And that looks to be 9 seconds as well. So 9 seconds. Describe the relationship between temperature of liquid hydrocarbon and the viscosity. So the higher the temperature, the less viscous. Of course, our time has gone down. But it's not a straight line, it's not a linear relationship, so we need to specify that. So it's a non-linear relationship, and the apparatus the student used in figure 2 could lead to a systematic error. Identify one source of this. So the one that jumped out to me was the fact that you're going to pour your warm hydrocarbon into this funnel, and it's probably going to be sitting there quite a long time. So I think it would cool down during the course of the experiment, so it would actually take longer than it should have done. So I'm going to say hydrocarbon would cool in the funnel, giving a longer time than it should. So you could insulate the funnel to overcome this. So insulate the funnel to overcome that. Okay, and finally we have question 10 about alkanes and hydrocarbons, crude oil. First question asks, complete the sentence. Hydrocarbons contain the elements, well, they're just hydrogen and carbon. Ethane is an alkane with a formula C2H6. Draw a ring around the correct answer to complete the sequence. So we're looking for a formula that matches this. So if you imagine 2 is the number of carbons, so it is double, so 2 times 2 is 4, add an extra 2 gets us 6, so that matches this one here. So alkanes, the formula is CnH2n plus 2. Next we're looking at what's called a fractional distillation column, where we put crude oil, which is a mixture of hydrocarbons, in the bottom. It's evaporated, and because there's a temperature gradient up the column, you have the fractions separating off because they've got different boiling points. So crude oil is evaporated. That's going to be our first marking point here. We've got to explain what happens. So crude oil evaporates, where it's put into the bottom. The tower cools nearer the top, so it's cooler at the top, warmer at the bottom. Fractions have different boiling points. So they condense and separate at different levels. So these are the 4 points we need to know. Lastly, so C, we have dodecane, so C12H26 from crude oil is cracked. So this means we're splitting up a long chain hydrocarbon. So generally short chain molecules are better for us, they make better fuels, they're easier to deal with, give us more energy, so we want more of the shorter chains. However, crude oil contains lots more long chains than we want, so we have to break them apart, so cracking. We start with C12H26, and that's broken down into 2 carbons, hydrocarbons. We've got 2 lots of C2, so 2 times 2 is 4, so I've got 4 carbons on the right, but I've got 12 on the left, so I must have 8 carbons over here, and then I've used 8 hydrogens, so that must be 18 hydrogens. So I've just taken 8 from 26 there. 2 conditions needed for cracking, so you need high temperatures to carry out the cracking reaction. So high temperatures, and you need the presence of a catalyst. You don't need to be able to name the catalyst, you just need to know that a catalyst is present. Okay, thank you very much.